You know that feeling, right? Your brain is just this massive tangled web of ideas. But when you try to explain something, it has to come out one single word at a time, in a straight line. Well, guess what? Today's most powerful AIs have that exact same problem. Today, we're going to explore a pretty radical new AI architecture that completely changes the structure of digital thought itself, taking it from a simple line and turning into a complex, intelligent web. And this right here is the heart of the whole issue. On one side, you've got how AI stores knowledge in these gigantic interconnected webs. We call them knowledge graphs, where everything is linked to everything else. But then, on the other side, look at how it actually reasons in a simple, step-by-step linear sequence, a chain of thought. This is what's known as the structural mismatch problem. And honestly, it's a massive bottleneck for AI development. So here's our game plan. First, we're really going to dig into this thinking mismatch. Then, we'll look at a wild new way for AI to reason in 3 completely different rhythms. After that, we'll see how it can literally learn to build its own web of logic on the fly. And then, the best part, we'll see how all these pieces snap together into one unified architecture. Finally, we'll explore what this all means, a whole new era of reasoning. All right, Section 1, the thinking mismatch. You can really think of it like this. The AI's internal brain, that complex knowledge graph, and its mouth, the linear output, they just don't speak the same language. So every single time the AI needs to think through a problem, it's forced to translate this beautiful, complex web of knowledge into a simple, flat line of text. And as you can imagine, a lot gets lost in that translation. And this isn't just me using an analogy. The research paper this is all based on puts it really bluntly. They call this mismark a source of lossy translations. I mean, think about trying to describe a complex 3D sculpture using only words. You're going to lose all the detail, the nuance, the precision, right? Well, for an AI, that means its accuracy goes down, and it becomes a whole lot harder for us humans to actually follow its logic. So, okay, how do we fix this? Well, the first part of the solution is to get the AI to reason in 3 distinct rhythms. So instead of just one single speed of thought, this new approach breaks the whole process down into different frequencies, kind of like the brain waves that are firing in our own minds right now. This image makes the concept super clear. This is the Universal Signal Decomposition Framework, or USDF. Just look at the leopard, the low-frequency signal that gives you the forest, the big picture, the overall shape and pose. Then the mid-frequency gives you the trees. You start to see the object's boundaries. And finally, the high frequency gives you the leaves, all the fine textures and sharp edges. It's all about seeing the exact same thing, but at multiple levels of detail, all at once. And this is just brilliant because it shows you exactly where the idea comes from. It's not just some clever programming trick for images. Nope, it's directly inspired by neuroscience. Our own brains process information using different frequency bands, kind of like what you see here. You've got the raw EEG signal being broken down into its low, mid, and high frequency parts. And this new AI architecture is trying to copy that exact same multi-layered processing. So let's actually give these rhythms some names. First, you've got the alpha band. This one's operating at a slow frequency. It's for the big picture stuff, the overall strategy, the context of the problem. Then you have the beta band, which handles medium rate updates. It's integrating patterns, connecting different ideas together. And finally, the gamma band. This is for the fast, local operations, the stuff that requires immediate precision and detail. Okay, so thinking in different rhythms, that's one half of the solution. The other half? It's even more radical. It's about an AI that doesn't just read a pre-made map of knowledge, but one that actively learns how to draw its own map of logic while it's thinking. And this is called self-graph reasoning. So the really critical idea behind self-graph reasoning, or SGR, is that the model isn't just following a path that someone else laid out. No, it learns to build its own reasoning structure as it goes. Every single node in this web is a premise or a conclusion, and the lines connecting them are the logical links. It's basically showing its work, not as a straight line, but as this rich, interconnected web of logic. And listen, this isn't just a cool idea on a whiteboard. It gets incredible results. I mean, get this. When they fine-tuned models with SGR, they saw a performance jump of more than 17%. And that's across 5 different really hard question-answering benchmarks. That is a massive leap. It's pretty much proof that letting an AI build its own logical web makes it significantly smarter. Okay, so we have these 2 incredibly powerful ingredients, right? Reasoning in different frequencies and an AI that can build its own webs of logic. Now, we get to the really exciting part, putting them together to create a truly new kind of AI brain. Which, of course, leads us to the big question. How do you actually combine these two revolutionary ideas, right? How do you make sure that the fast, twitchy gamma band reasoning doesn't just completely derail the slow, strategic alpha band planning? How do you make the whole thing work together in a way that's stable and, governable? And the answer is this: the frequency-governed self-graph reasoning architecture, or FGSGR. Now, I know, it looks complex, but the key idea is how it orchestrates everything. Those rhythms we talked about, alpha, beta, and gamma, they literally govern how the AI builds its reasoning web. The slow rhythms manage the overall structure and the long-term goals, while the fast rhythms are busy filling in the immediate details, all without interfering with each other. It's a unified system that finally allows for hierarchical thinking, and, this is crucial, it builds safety and interpretability right into its very core. This whole thing works because it's built on four really elegant principles. First, structural homogeneity. This just means that knowledge and reasoning finally speak the same language, the language of graphs. No more lossy translation. Second, temporal respect. The different thinking speeds stay in their own lanes. Third, governance integration. Safety isn't some add-on at the end. It is woven into the very process of how the AI thinks. And finally, internalized construction. The AI is the architect of its own thought process. Okay, so now that we've seen how this new kind of AI brain is built, what can it actually do? This brings us to the payoff. We're going to explore the absolutely groundbreaking new capabilities that get unlocked when an AI can fundamentally change how it thinks. This table just says it all, doesn't it? Traditional chain of thought can only do one thing: think in a straight line. Tree of thought added branching, which was a big step. But now look at FGSGR. It can do parallel synthesis, exploring multiple lines of thought at once and then weaving them together. It can do cyclic refinement, looping back to improve an earlier idea. It can integrate thoughts across different chains and different timescales. I mean, this is a genuine quantum leap in reasoning ability. Let's make this super concrete. Think about an autonomous vehicle. The slow alpha band holds the high-level mission: arrive at destination. Simple. The medium beta band is handling the route planning, updating based on traffic. But it's the fast gamma band that lets the car react instantly to a sudden obstacle, like another car just cutting right in front of it. All three rhythms are working together in perfect harmony, making sure that the car's instant reaction doesn't make it forget its ultimate destination. The possibilities this unlocks are, well, they're staggering. Think about it. Temporal coherence means you have an AI that's strategically consistent over long periods of time. Multi-agent negotiation could mean two AIs building arguments against each other in real time. Self-modifying topologies, that means an AI can literally analyze its own thinking process and improve itself. And maybe the most exciting part, this architecture maps directly onto neuromorphic brain-like hardware, which promises incredible leaps in efficiency. We've spent so much time asking what an AI will think, but by moving from these simple linear chains to these dynamic, multi-frequency webs, we are fundamentally changing the structure of digital thought itself. So that leaves us with a much, much more profound question. If an AI can fundamentally change how it thinks, what will it think of next?